After this very entertaining lecture by Andrea, so let's go back to boring random matrices, if you like. So let me start just by just a quick recap of what we did yesterday. So yesterday I introduced this two ensembles of random matrices. So roughly speaking, these are the with real spectrum. I mean, with real eigenvalue spectrum. So these are called the Wigner matrices, and this is the rotational invariant probability distribution. So here you choose the entries of your matrices completely independent random variables drawn from some distribution, and in this second case, you choose the distribution of the entries such that it's invariant under an orthogonal transformation. And I've also mentioned that there's only one particular class of distribution which is Wigner as well as rotational invariant, and this is the Gaussian distribution with a properly chosen variance. So the probability distribution of the entry is proportional to trace of x square. Okay, so you can think of it as rotational invariant, as well as that you can think of that each entry, independent entries have been chosen independently from a Gaussian distribution with specified variances. Okay, and then I also mentioned that numerically, so this is the advantage, is that it's numerically very easy to generate such matrices. You just choose the entries independently from random variable and you construct your matrix, and you can diagonalize and get the eigenvalues and so on. But this one is numerically very hard, easy. This is numerically very hard except for the Gaussian, because for example, if you add a trace x fourth term, then they get horribly correlated, the entries. So numerically it's hard. But analytically, if you want to calculate the distribution of eigenvalues, so by distribution of eigenvalues, I mean the joint distribution of the eigenvalues. So usually for Wigner matrices is very hard, and it's relatively easy for, so this is analytically. But here we'll see that the rotational invariance of the ensemble makes it easier to compute the joint distribution of eigenvalues. And in fact, what we'll see today, that's what I plan to do today, to show you how to compute the joint distribution of eigenvalues for rotational invariant systems. And we'll see that as a result, the eigenvalues and eigenvectors will completely decouple from each other. So at the end of this first half, so after deriving, so the goal is to compute the JPDF, joint probability density function, of this n eigenvalues for this class rotationally invariant ensemble. So this is what we'll do, and then I'll just I'll finish with a comment or remark on essentially 1D disordered systems, which sort of will be sort of tie up with the next week's lecture of Marcus Muller. Okay, so we want to compute, so basically, these rotational invariant ensembles, so you have given me the joint distribution of the entries. I'll just write a shorthand notation like this. Okay, so this is given to me, and I want to calculate the distribution of eigenvalues. Okay, and so let's take the simple case first, a real symmetric matrix. So this is not an easy problem. Okay, it takes a while just to appreciate that. So let's again think of, because it's always instructive, at least for me, I always find it instructive to look at the 2x2 matrices. Okay, so we have a real in general, of course, you will have n by n matrices. Okay. So, but let's say even for these two by two matrices, okay. So what you have given me is, let's say, just the Gaussian, okay, just a simple case of Gaussian. So joint distribution of, so I have three independent variables, x11, x12, x22, and suppose you have given me up to a normalization constant. This is just a Gaussian, independent Gaussian. So x1 square plus x22 square plus 2 times x12 square, because this is trace of x squared, so there is a factor 2 which comes in. Okay, so you have given me this, and I want to compute the distribution of eigenvalues. There are two eigenvalues, okay. So clearly, I mean, given particular relation, you will calculate the eigenvalues just by looking at the determinant. Let's see, standard stuff. Just to appreciate the, naive difficulty. So if I want to calculate this, so I will put this determinant equal to 0. So this gives me a quadratic equation, and you can get the two eigenvalues explicitly as functions of the entries. So let's see. So this will be just x11 plus x22 plus square root of x11 minus x22 square plus 4x12 square divided by 2, and lambda 2 will be the other root, which is minus this. Okay. So these guys are Gaussian distributed. So naively, then to compute the joint distribution of eigenvalues, what we'll do is this, therefore, will be just delta function of lambda 1 minus this function here. So let me call it lambda 1x. I mean, just these functions. And then you have this delta 2, lambda 2 of this function. And then you have to multiply it by the probability distribution of this function. And integrate over all possibilities. Right? This would give me this is what naively will do. I mean, if I give you some object and which is a function of something else, and that something else has a distribution, a random variable, then to compute the distribution, this is what you will do. Right? I mean, it just counts whenever this is equal to lambda 1 and lambda 2. How many possibilities that there are at lambda 1, lambda 2. But you see immediately that, I mean, it's horrible. Even for 2 by 2 matrix, this is horribly complicated. I mean, if you, how will you do this? I mean, it's triple integral and looks very complicated. Okay, and then if you go to n by n matrices, then you will have this a polynomial of degree n whose roots will be these functions, and if you try to compute this way, it's really hopeless task, right? So how does one go about it? And so the trick is actually not to do it this way. So in the end, you will see that answer is very simple. Okay, so answer for this case eventually will be, and you can check. I mean, by Mathematica, if you just put it this way, the answer would be just this. Okay. So there will be lambda 1 square by 2, lambda 2 square by 2 times modulus of lambda 1 minus lambda 2. But to see this emerging from this, it looks horrible, right? So how do we actually derive this result? So there is a trick, and the trick is just by change of variable, proper change of variable. Physics is always about change of variables. I mean, you have to always find the right change of variable. Okay. Okay. So, okay, I'll just discuss the general case first. So let's say I have an n by n real symmetric matrix, x11, x12, etc. And this is just the symmetric counterpart. Okay, so I have, these are my independent degrees of freedom. In this dx, I have all these elements. Okay, so how many are there? So in general, if I have an n by n real symmetric matrix, so the number of independent degrees of freedom so it's just 1 plus 2 plus 3 up to n, right? So this is n into n plus 1 over 2. So these are my degrees of freedom, n into n plus 1 over 2 variables. And I want to make a change of variable to another set of n into n plus 1 over 2 variables. Okay. So what can I do? So this is the idea of change of variables. So the change of variables, so you are going from this xij with I less than j, these degrees of freedom, to another set of degrees of variables. Okay. So what I'll do now, so what I know is that given a real symmetric matrix, there is always an orthogonal transformation, okay, which I'll call by O. So this orthogonal transformation, if I take O transpose XO, that diagonalizes this matrix, right? So this means it's a diagonal matrix lambda 1, lambda n. And you also know that this matrix O, which is the guy that diagonalizes this matrix, its columns are just the eigenvectors. Okay. So the idea is then that to make this change of variables, so I first choose the eigenvalues because they are also random variables. Okay. But then I'm short of this because I have n into n plus 1 over 2 variables and there are only n eigenvalues. So I need some more variables. So what are these some more variables? So these are just the eigenvectors, independent elements of the eigenvectors. How many of them are there? Okay. So collectively, I mean, I'll just, if you call this Oij, I'll choose the right number of eigenvector degrees of freedom. How many eigenvector degrees of freedom are there? So you see this matrix O, which is an eigenvector. So what is so number of independent entries in this matrix Oij. So how many total number of degrees of freedom is n square, right? Because I have n by n columns. So total number of elements inside this matrix is n squared. Okay, but you have some constraints because these eigenvalue, the eigenvectors, first of all, they are orthonormal. That means sum of these squares of these elements is 1 for each of them. So there are n such constraints, and then also that they are orthogonal to each other, right? So the dot product of these vectors, column vectors, they are all 0. So how many constraints are there? So this is total number of degrees of freedom, and so if I subtract off the number of constraints, so number of constraints will be, if I first take this column here, so how many are there? So I have orthonormality, which is normalization is 1, and then I have another n minus 1 orthogonal product. So therefore for this guy I have n constraints. For this guy I'll have n minus 1 constraint because I've already taken into account this guy. So it's just going this way. So basically this will be n plus n minus 1 plus n minus 2 up to 1. Okay. So this is the total number of entries, and then you have so many constraints. So the number of independent degrees of freedom in the eigenvectors, eigenvector matrix, this orthogonal matrix, is therefore this, and this is just n square minus n into n plus 1 over 2, which is n into n minus 1 over 2. Okay. So here I'll choose this n times n into n minus 1 over 2 degrees of freedom of the orthogonal transformation, and I have these n eigenvalues in addition. So the total, if I add these two up, is exactly n into n plus 1 over 2, which is what I need, because I have n into n plus 1 over 2 in the original matrix. Okay. So this is at least, this is a good set of change of variables. At least it has the right number. And so the idea is to make this change of variable from the entries into the eigenvalues and the eigenvector degrees of freedom. Okay. And then, so once you know this, so you see that generally speaking, so you have this P of xij times this product of dxij I less than equal to j. So from this, you are making a change of variable, and you are going into, this n variables times this yj variables, and then here you will have d lambda 1, d lambda n, and then you have this d of yj product I less than j. I mean, by I less than j, I mean this product, I mean all these independent eigenvector degrees of freedom. And when you make this change of variables, so there will be, a Jacobian term, of course, which involves this change of variables from Jacobian. I mean, symbolically, I'm writing Jacobian from going from x to this lambda o. Okay. And then, so you know this, so you write down this, and then finally the idea is that, okay, if you can compute this object, this Jacobian and this object here, and then you integrate over the eigenvector degrees of freedom, and that will give you the marginal distribution of the eigenvalues. Okay. So how does it work? So again, I'll just do it just to give you the general idea. It's enough to do the 2 by 2 case, and you can then generalize it quite easily for n by n case. Okay, so let's start with the 2 by 2 matrix. So I have this. So here I have 3 degrees of freedom, and so when I, again the change of variable, so I'll get 2 eigenvalues and 1 eigenvector degrees of freedom, which, okay, so what you know is that, as I told you in the last lecture, that this I can always, again my orthogonal transformation here, that diagonalizes this matrix, I can always parameterize it by an angle. So this will be cosine theta minus sine theta, cosine theta. Okay. So what you see here is this degree of freedom here. There is only one degree of freedom, which is this theta, which characterizes this orthogonal matrix. I mean, I could take cos theta, but I mean it's easier to take theta basically. Okay. So these are the 2 eigenvectors which are orthonormal to each other, and you have these 2 eigenvalues. Okay. And what we know is, what is given to us is again this distribution, which is up to some normalization, minus half x1 square plus x22 square plus 2x12 square. Okay, so let's just see it explicitly, just to get familiarized with the idea. So I told you that this x here, so I can just invert it. So x will be, maybe I'll write it this way, minus. Okay. So x will be just O lambda O transpose, right? Just inverting this, because then O transpose is orthogonal matrix. So let's write it down explicitly, therefore. So this is just 2 by 2 matrix, cosine theta, sine theta, and I have, this is a diagonal matrix, so lambda 1, 0, 0, lambda 2, and that guy is cosine theta minus sine theta O transpose. Okay. So your original matrix X, you can write it this way. So then you can just read off, just multiply these 3 matrices, and you can write down, so this thing if you multiply, so this is lambda 1 cosine square theta plus lambda 2 sine square theta, lambda 1 minus lambda 2 cosine theta sine theta. Okay, so this is my x11, x12, x12, x22. Okay, so now so this guy, so P of x1, x12, x22, dx1 so this is equal to that. But you see this guy here, I can write, because this is just a trace of x square, so I can write in terms of the eigenvalues, this is just lambda 1 square plus lambda 2 square, right? So this part, the functional part of the measure is completely invariant. This is the rotational invariance, so which means that you can express only in terms of eigenvalues. Okay, so therefore, this object, I'm just rewriting this in terms of eigenvalues. And then I'll have this Jacobian term. So all I have to do is to calculate this Jacobian term, okay, and then I have to integrate over theta, eigenvector degrees of freedom, to get the joint distribution of lambda 1 and lambda 2, right? So let's compute this Jacobian term. So you have this, this relation that is, this is a little bit, details, but I sort of, I'm doing it so that, you sort of see exactly how it comes about. So this is my relation, change of variables, right? So the Jacobian is just del x11 del lambda 1 del x22 del lambda 1. Okay, I'm writing it this way, but it doesn't have to be. Right, so this is your Jacobian matrix. Okay, so you can just read off from this relation. So this will be just cosine square theta, sine square theta, cosine theta, sine theta, sine square theta, cosine square theta minus cos theta, sine theta, and then you have a minus 2 lambda 1 minus lambda 2 times cos theta sine theta Here you'll have a 2 lambda 1 minus lambda 2 cos theta sin theta. This is multiplying. Okay. This. And the last guy is just cos square theta minus sin square theta. Okay, so this is the, so you have to calculate the determinant of this, right? So Jacobian is this matrix, but I'm calculating its determinant. So this determinant of this. So first thing you notice that when you want to calculate the determinant, you see this lambda 1 minus lambda 2 is common in all the rows here, okay? So on all the columns, 3 columns, so you can just take it out outside the factor, okay? And the rest is just a, a matrix which, determinant of a matrix which involves only theta, and you can, trivially evaluate these things and you just find it's 1. Okay? So first thing that you notice is that this Jacobian is completely independent of theta. It depends only on the eigenvalues. Okay? So then you are done. I'll come back to this comment later. So okay, there may be the factor 2 pi here, so d theta. So now you see that if I can trivially now integrate over the eigenvector degrees of freedom. So if I integrate over d theta, this just gives a factor 1. So therefore, you sort of come to this result up to a normalization constant. Okay, there is the overall normalization constant here. Okay, maybe I can include this 2 pi in that. So up to a normalization constant. So this is just yep.
So I have a question about methods.
Yes.
To prove, say, the extension of this theorem or the computation of this Jacobian
Yes.
higher n.
Yes.
So I noticed this determinant you have to calculate there is almost the same as we obtained yesterday to prove that the eigenmeasure is
Yes. Yes, but this is not exactly same because you see this, here I'm choosing a particular orthogonal transformation which diagonalizes this, okay? So this is not the same as yesterday. Yesterday was, what I said is that if you make any similarity transformation, then the Lebesgue measure is invariant, basically, okay? But it's not, but here I'm making a particular, given my matrix, there's a particular orthogonal transformation which diagonalizes this matrix, and I'm choosing the elements of that matrix, okay? And so this Jacobian is not the same as the Jacobian of the similarity transformation that we wrote down, because that involved only those similarity transformations. It didn't involve any eigenvalues, okay? But here it involves the eigenvalues also, okay? Yeah.
Is there an easy way to see, so for a non-degenerate spectrum, that this choice of eigenvalues, that always gives a non-singular Jacobian? That's
Non.
that transformation is.
Yeah. Determinant non-zero.
For a non-degenerate spectrum. So that these are always independent variables, so to speak.
Which are independent variables? The entries. Yes.
Collection.
Exactly. Now I'll come to that in just in a minute. I'll come to that. Okay. So, so basically, you see that. So there are 2 comments here. So first thing is that you see that even though the entries were independent for the Gaussian case, the eigenvalues are actually correlated. Okay. So if this term was not there, then the 2 eigenvalues would be completely independent. But because of this term, you see that they repel each other. That means the probability that the 2 eigenvalues will be close to each other goes to 0, right? With a power 1, because it's a real symmetric matrix, okay? And so this is the first instance that you see that explicitly, that the joint distribution of the eigenvalues involves a term which mixes, so this is the sort of term responsible for correlation between eigenvalues. If I didn't have this term, then it will be completely independent again, okay, eigenvalues. But now this is the case where the eigenvalues are correlated, okay. Now, the important thing here, I mean, you can ask that, so now the statement is that, I mean, even without doing this calculation, you see that this Jacobian term here, you can argue that this should be I mean, here you see this explicitly coming out, but clearly, by rotational invariance, and again, I mean, I'll explain in a minute. So this guy, you would expect, to start with, that it can depend only on eigenvalues and not on eigenvectors. Okay, why is that for the rotational invariant ensembles? Because you see this. Okay, I mean, I did this exercise to show you explicitly, demonstrate, but you could have argued without doing any computation that this Jacobian should involve only eigenvalues and not eigenvectors. Okay, statement is that this Jacobian in general, it's only a function of eigenvalues, and it's completely independent of these eigenvector degrees of freedom. Okay, and the reason is, okay, so what am I doing? I mean, I have a matrix X here, right? And I made sort of symbolically, I mean, I made an orthogonal transformation O, which brings me to a diagonal matrix. Okay, and this Jacobian is just this change of variables, which involves the eigenvalues as well as eigenvectors. Now, imagine, I mean, yesterday I told you that, I mean, when you make a similarity transformation, the eigenvalues do not change, but the eigenvectors, they get rotated, right? So now imagine that, I make an orthogonal transformation, some other S orthogonal transformation to X, to come to by a similarity transformation to another matrix Y. So this matrix Y will have the same eigenvalues as X, okay? But the eigenvectors of this guy will be different. But here, I can again, make this transformation now by a different, matrix. I mean, if I call it OX, this will be OY, which will diagonalize it and bring it here, okay? Now, the point is that we have already seen that the Lebesgue measure or the invariant measure, this dx under similarity transformation, and this is why this was important to show that this object, it doesn't change. Dx is same as dy, okay? So, which means that, and then, this dx, you are writing in terms of the eigenvalues, right? D lambda n times d whatever, d theta, let's say. Okay, let's take the 2 by 2 example, okay? D theta. So this, and then it involves the Jacobian. Imagine that this Jacobian depends on lambda 1, lambda 2 theta, okay? So the point is that this dx equal to dy, so that means, this object here, if it depended on theta, so dy will have a theta prime, let's say. So I just make a shift theta to theta prime, and then, it will be, this should be equal to theta plus some, some phi, just make a rotation basically. Okay. So because this is just a rotation, so, it's just another theta basically, okay. And because this invariant, under similarity transformation, this is invariant, so therefore this should be equal to this, and so you can choose this phi anything you like, so this should be always, the same. So this means that, this j, lambda 1, lambda 2 theta cannot depend on theta, okay? So this just sort of proves that, I didn't prove it kind of rigorously, but just to give you the argument that this is just, that the Jacobian for rotational invariant ensembles, this is totally independent of the eigenvector degrees of freedom. Okay, it only depends on eigenvalues, and this is what you see explicitly here, that the eigenvalue and eigen set of smaller set of random variables, which is n's eigenvalues, and I can calculate what is their joint distribution, and so for 2 by 2 this is given by this. Now if you do this calculation for a n by n matrix. I'll give you the result, I won't give you the proof. It's a little bit complicated, but it's not that complicated. There are some tricks to do that, but okay, I will not have time to do this. So for n by n matrices, so first for Gaussian, okay. So again up to some normalization constant which depends on this. So it will be half times summation lambda I square. You see this guy here is exactly same because your general thing will be to the power minus half trace x square, and for n by n matrices trace x square is just summation lambda I square. Okay. So this part, the p part, which is the functional part basically, so that only depends on eigenvalues because this is invariant under rotation. It has to be a function of trace of x square or x trace of x fourth, etc. So therefore this part totally remains, it's only depends on eigenvalues. And then there's the Jacobian part, and the Jacobian part, generalization of that will be, I'm not proving this. So for example, if you take 2 by 2, it's just lambda 1 minus lambda 2. If you take 3 by 3, it will be lambda 1 minus lambda 2, lambda 2 minus lambda 3, lambda 3 minus lambda 1. Okay. So every pair gets a factor which is the difference of eigenvalues. So this means the eigenvalues all repel each other, and this is for real symmetric matrix. Okay. So this is the Jacobian. Okay. And again, the eigenvector degrees of freedom completely decouples. So like this theta, in general, this will be dy yj, which means that these are just, if you think of this O, this orthogonal matrix, which is the eigenvector matrix. Okay. So the columns, so they are just basically random vectors. Okay. So if I look at the eigenvector, so eigenvectors, eigenvalues and eigenvectors don't talk to each other. Okay. So if I take any particular eigenvector, so it's a column vector, right, with let's say entries like this. It does not depend on the eigenvalue. Okay. So for example, for 2 by 2, you'll have 2 orthonormal eigenvectors, and only thing that is there, these objects are completely uniform random numbers because in front of this there is nothing. It's a uniform measure, except that it has to be normalized. Okay. So it's a random vector, if you like, random unit vector in the n-dimensional sphere, right? So it's like a unit vector, so eigenvector on this n-dimensional sphere, and with unit norm, and but otherwise they are completely random numbers basically, just satisfying this constraint. Okay. So if you want, if you want to calculate the joint distribution of the entries of an eigenvector, so this is again up to some normalization constant, is just delta function of summation ai square minus 1. Okay. So which means typically that these eigenvectors, they will be everywhere. So, and I'll come back to at the end of the lecture to sort of say that this is sort of, it shows that these eigenvectors are completely delocalized. I'll be precise what I mean by that. Okay. All right. So the main result therefore is what we learned is that once you diagonalize for Gaussian matrices, real Gaussian matrices, so you have, this is the sort of, for real symmetric matrices, this is the result. Now if you take, instead of Gaussian, and this is sort of goes back to your question, that suppose I take something like minus half trace x square, but I add a term trace x fourth, or in general any potential of this, right? So in this case, the entries are completely uncorrelated because of the x fourth term. Okay, so they are completely correlated. But nevertheless, because it's rotationally invariant, when you write in terms of the eigenvalues and eigenvector degrees of freedom, you see this part just becomes summation lambda I square times summation lambda I4, okay, because trace of x4. And the Jacobian part, it doesn't depend on this weight. So Jacobian is just again going to be lambda I minus lambda j I less than j. Okay. And again the eigenvectors degrees of freedom. So this part of working with the Jacobian and the volume element, that doesn't really depend on this. This is only dependent on the eigenvalues. So therefore, so what you see is that for any rotational invariant ensemble, where in general I can write down this as some trace of some polynomial of this matrix X, so for example x squared plus x fourth plus x sixth, etc. So then the joint distribution for such matrix models will be up to a normalization constant, will be again half summation I equal to 1 to n v of lambda I, because all the trace x square, x fourth, x sixth you can write in terms of the lambda i's, so it just becomes the same function v of lambda I, and again you will have this same Jacobian factor. Sorry, I mean I'm writing probability density, so it's fine. Okay, so this is the sort of so it doesn't have to be completely independent entries. It can be any rotational invariant measure, and it just translates into purely in terms of eigenvalues into this. And the only non-trivial factor which gives rise to the correlation, it actually comes from the Jacobian. Okay, and now the thing is that, of course, I mean this is a completely mathematical calculation, right? You don't get any physical intuition why the eigenvalues repel each other. Okay, and I mean, as I go along, I'll in the second half today, I mean I'll do what is called the Dyson Brownian motion, and then you will see that where this term comes from and why they repel each other. And later when you do fermions in a trap, there you will see that this is a consequence of the physical Pauli exclusion principle between the fermions. Okay, so this is the result for real symmetric matrix. Now we can do the same exercise, and this is an exercise. Do the 2 by 2 case for a complex Hermitian matrix. Okay, so take this x dagger equal to x. Take the Gaussian again, so it will be minus half trace of x square 2 by 2, and just carry out the same calculation and show that so this is the exercise. Show that this will be again up to some normalization constant. It will be minus half but instead of lambda 1 minus lambda 2, now it will be lambda 1 minus lambda 2 square. So when you calculate the Jacobian, so you will see that instead of absolute value of lambda 1 minus lambda 2, it just becomes lambda 1 minus lambda 2 square. And if you go to the n by n case, so this is the Gaussian. So this is what is called the GOE, Gaussian orthogonal ensemble. And the case of GOE, which is the complex Hermitian case, so general n by n case, again up to some normalization constant, this will be half summation lambda I square, and then lambda I minus lambda j mod square. And then there's a third class, which is same thing again. If you take an arbitrary potential V, then it will be exactly same factor. Only thing the Jacobian will just become square. And then the last one is this quaternion case, complex quaternion matrices, which I did not define, but if you work it out, So this is called the GAC, Gaussian symplectic ensemble. So there you will find that the joint distribution of eigenvalues again up to some normalization. And now it just becomes to the power 4. So Jacobian just becomes lambda I minus lambda j to the power 4. Okay. So therefore, for all the these three standard Gaussian ensembles, so this is the sort of one of the central result in random matrix theory, that this up to some normalization, which is normally written as 1 over Zn, okay, and then you will have e to the power minus half summation lambda I square. And as I said, if you take an arbitrary potential, you can replace this harmonic potential by v of lambda, and then you will have this factor here, which is this Jacobian factor. And I write this index beta here, and for a reason you will see immediately. So beta equal to 1 for real symmetric matrix, that is the GOE. So this beta is quantized. Okay, it has 3 values for GOE and equal to 4 for GSE. Okay, so this is called the Dyson index. And again, I re-emphasize again that this is the term which makes the eigenvalues correlated. If you did not have this term, then they will be completely independent Gaussian variables, and then you can calculate any observable, whatever you want to calculate, very easily, trivially. Okay, and for instance, if you calculate the distance between eigenvalues, spacing distribution, you will get an exponential distribution. I'll do that later. And whereas because of this correlation here, this is what makes the Wigner-Dyson, this is called the Wigner-Dyson distribution, and this is different from the independent distribution. It's a correlation which is very important. Okay, so now once you have this result, okay, now you see that this is, we use the fact that it's rotationally invariant ensemble very crucially. If we didn't have that, like for Wigner matrices, I could not have done this computation. Okay, so for Wigner matrices, you see, it's very difficult to derive the joint distribution, and nobody knows in general how to do it except for some special cases. Okay, so so that's the sort of difference. So this has the advantage that you can analytically compute the joint distribution of eigenvalues. Okay, and once you have that, see, after that it's a problem of statistical mechanics that you give me the joint distribution. If you want to calculate any observable involving these lambdas, in principle you can actually compute this. So this is like for example, if you think of Ising model, once it tells you that you are in a thermal bath and you are in equilibrium, morally similar to, let's say, the Ising model. Okay, so Ising model, you will have the energy function for a given spin configuration. So energy function is just, let's say, J S I S J, let's say nearest neighbors. And once you have this energy for different spin configurations, and then Boltzmann tells you that in thermal equilibrium, the probability of a given configuration of the spins, again up to a normalization constant, which is the partition function, times exponential minus beta times this energy, right? So the probability of different configurations, but then to compute more observables like magnetization or other things, correlation functions, is not always trivial. Okay, but at least what the starting point is, what the probability of a given configuration is this. After that, calculating the explicitly the the correlation functions or other observables, magnetization, etc., that involves, mathematical physics. I mean, you have to know techniques how to compute that. But at least the starting point is there. Okay. So in the same sense here, that for rotational invariant ensembles, if I want to calculate think of this is like this analogous to the spin variables. It at least gives you the probability of a given configuration of lambdas. So I have a starting point, and once I have that, I mean, I can try to calculate observables again using mathematical tricks or mathematical physics or statistical mechanics of this set of variables. Okay, but at least I have the starting point. But for Wigner matrices, I don't even have a starting point. I don't even know what is the joint distribution of eigenvalues. And in fact, in that case, the eigenvalues and eigenvectors are quite strongly correlated, and so you cannot have this decoupling between eigenvectors and eigenvalues. So let me just make a few additional remarks. So first remark is, I mean, for these things, once you have this result, so remark number one, as I already mentioned, that it's a strongly correlated eigenvalues, and in fact there's a level repulsion. By level repulsion, what it means is that the two eigenvalues do not like to be next to each other. The probability for that, because this beta is positive, so probability for that is very, very small. Okay. The second remark is that, so this object, I can go even further and write it as a Coulomb gas. So this is called the Dyson Coulomb gas, and I'll tell you what this is, or sometimes called the log gas. So you see this object here. Okay, so you can always write x to the power beta as e to the power beta log x, right? So then I can write down this joint distribution There is a factor half because I made I less than j. I just included the other term and write I not equal to j. So you have to divide by factor 2. Okay. So I can write it this way. And furthermore, I can I can always rescale this lambda i's by square root of beta times lambda I. Okay. So if I rescale that, then I get a factor beta here, and this is the additional constant factor which you can always absorb in the normalization constant. So under rescaling, I can always write down this as exponential minus beta by 2 summation lambda I square plus beta by 2 . So this is so I can write it like a Boltzmann factor, like in the Ising model. Okay, but now this beta, I mean, remember that this beta was quantized, of course. Okay, but of course there are now, people know there are these things called beta n's. There are random matrices for which you can actually have the joint distribution with a continuous value of beta. So for the moment, let's think of this beta as a continuous parameter. Then you can think of this beta like an inverse temperature. That's the reason why the this index is denoted by beta. And then I have. So what does this mean? So these lambda i's are just a real eigenvalues. So they are lying on a 1D line, like points on a line, right? So you can think of them as charge, and there is an energy associated to each configuration, and this energy is just half summation lambda I square minus half times I not equal to j log of lambda I minus lambda j. So you can think of this lambda i's as the position of charged particles on a line. Okay. Now there are two terms in this energy function. So there is an external term, which is like each of them is sitting in an external harmonic potential, and they feel the energy. So it's a completely additive term. So this, if you like, this is the analog in the morally, it's analog in the Ising model. If you put a, let's say, magnetic field, external field, so this is the sort of analog of that. So there is an energy, there is a external potential energy, and then there's an interaction term, and this interaction term tells me that, you know, these are, repelling each other. So all the, if I think of these as charges, every pair of charge, they repel each other by this logarithmic interaction. Okay, so, and that's the name log gas comes from. So logarithmic repulsion. So it's not really Coulomb gas, because, the logarithm repulsion will be true for Coulomb gas in 2D. But if you take the 1D Coulomb gas, it will be linear. The solution of, Laplacian is a linear function. But here it's a log. So these are like, if you like, two-dimensional charges, but they're confined on a line, and then they are repelling each other by the two-dimensional Coulomb interaction. But they're confined on a real line because these are real eigenvalues. Okay. So anyway, this is this sort of long-range interaction. Okay. So this is long range because every pair is interacting with every other pair. So again, think of the Ising model. If you just, put a Jij inside this, and morally, it's sort of similar. Like if you put the Ising model with long-range interaction, and then put in a magnetic field. So this system is something like that. Not exactly the same, but, here you have the charges, their positions on a line, and the continuum, this is not on a lattice. And they are repelling each other by this Coulomb repulsion, two-dimensional Coulomb repulsion, log repulsion. And then they're sitting in an external confining harmonic potential. If you don't take Gaussian, if you take some other rotational invariant ensemble with V of lambda I here, you just replace this by V of lambda I. Okay, so that is like this. So the potential there, which appears in the matrix potential, that appears as a confining potential in this Coulomb gas problem. Okay. Okay, so this is the, so now we have to do the statistical mechanics of this Coulomb gas basically. Okay, so this is, so once you have this, this joint distribution of the eigenvalues, you can interpret this as a Boltzmann weight in a temperature beta, inverse temperature beta, and with this energy function. And you want to calculate, various observables like correlation functions, the gap between the nearest neighbor eigenvalues, largest eigenvalue, etc., etc. Okay, so everything is contained. Like Herbert mentioned yesterday, that if you look at the largest eigenvalue, so that will be the what is called the Tracy-Widom distribution. It's all there. I mean, this is just the weight function, probability of a given configuration. So you have to just find out the given this joint distribution of eigenvalues, you want to calculate the largest eigenvalue. So you can actually knowing this weight function in principle you can write. I will do that explicitly later. But okay, this is the Coulomb gas. And so what will happen? So I mean, roughly speaking, I'll do it in detail later, but what we'll see is that, there are the two competing terms, right? So what this guy is trying to do? So this confining potential is trying to push all these charges toward the center. So this is the origin. So they want to minimize this energy for large n. So therefore, they are just trying to push all the particles towards the center of the trap. But then the repulsion term, they don't like the particles to be next to each other, right? There's a repulsion between eigenvalues. So they're trying to push them apart, okay? So these two terms actually compete with each other. There's a competition between these two terms. So you can actually, just do sort of just hand waving calculation just to estimate what is the typical scale, what is the typical size of the eigenvalues if I use this, okay? So, for example, this term here, if you take a lambda typical, so there is a square, and there are n such terms. So the first term here, the energy, it scales like lambda typical square times n, okay? And the second term, because this is a pair interaction, so there will be n into n minus 1 pairs. So roughly speaking, if you ignore this logarithmic and all this, roughly speaking for large n, the second term scales like order n square. Okay. So therefore, just by matching these two energies, if they have to compete with each other, so then the typical scale of lambda is of order square root of n. Okay. So if you just diagonalize the eigenvalues, and you'll see the typical size of the eigenvalue is of order square root of n. And what you would expect in the large n limit, therefore, because of the competition, see, they cannot all sit down at the center and become a delta function, right? So, because this is trying to spread them apart. And of course, they cannot go to spread all the way up to infinity, because then the confining potential is trying to, it will cost too much energy for this guy. Okay. So what we'll see is that on an average, the typical configuration of the system, this is the lambda axis here, it will settle down into a density which looks like this. Okay. And with a finite support, because as I said, it cannot come to all delta function at 0. It cannot be spread uniformly all over the space, because these two terms, competition between these two terms makes the system converge to a density of states which is called the Wigner's semicircular law, and I'll do it in detail later. Okay. So what this means is that how will I calculate the density? So density, I'm defining like this. So given this joint distribution, so the density is defined, density normalized to 1 is defined like this. Where this expectation value is with respect to this probability distribution. Okay. So you see, this object is normalized to 1 by definition, right? So if I calculate this, should be equal to 1. So it just tells me what fraction of eigenvalues are there between lambda and lambda plus d lambda on an average. Okay. And we have already seen that typically the scale of these things is root n. Okay. So this is a function of two variables, lambda and n. So in the large n limit, what happens is that it will be some scaling function of lambda over root n, because I just showed you that the typical scale is square root of n. So it should be lambda over root n, but it should be normalized to 1. So you should have a 1 over square root of n outside in order to normalize it, such that the function fz dz is 1. Okay. And in fact, so we'll see later that this function f z, you have to rescale beta also. So, but I'll do that later. Just mentioning this result. So this just becomes 1 over pi square root of 2 minus z square. Okay. So which means that it vanishes. So I'm plotting here the row of lambda n. So when you scale all these things so that all the eigenvalues of order 1, then it's just it's a finite. It's called semicircle because of this law here. So which means there will be more eigenvalues near the center, near the trap center, and there will be lesser and lesser eigenvalues. The density will fall as you go, and beyond root 2, on an average, there won't be any eigenvalues. Okay. So you see already that the largest eigenvalue on an average will be root 2 times root n. So in this case, so this will be root 2n. Okay. But then there will be fluctuation. This is exactly the deterministic term that Herbert was writing down in his, for the KPZ height, for example, there will be average velocity times, there it was v times t, but this is just this deterministic part. And then there will be a fluctuating part. So if I write this lambda max as a random variable, then this will be root 2n, and we'll see that there will be a fluctuating part which will be n to the power minus 1/6, and there's a very simple explanation for that. I'll come to that later, times this Tracy-Widom distribution times the random variable of order 1, which is Tracy-Williams distribution. So this is the age statistics here, either here or that side, symmetrically. Okay, but this is the sort of picture of this this Coulomb gas. Okay, so this is remark number 2, and yeah. We don't give a break. Okay, fine. Sorry. Okay, all right. So we'll come back to this.